let's talk about what goes on with an inverse function. Today's topic is all about inverse functions. So first off, what is that? What's an inverse function? I want to make it real for you because the questions are going to they're going to push us with a little bit of tricky questions about halfway or 2/3 of the way through, where it'll be really helpful if we really have a real sense of things. So let me give you a real sense of things. Functions, this sine is a function. Sine, cosine, tangent, secant, cosecant, whatever the other one is. They're all functions. They're all now, what do I mean function? As you move higher in math, next comes pre-calculus. It's all about, a lot of it is about functions. So let's talk about the basic idea of what I think you know, but let me strengthen what you know. A toaster. I always want to take something real that we all deal with, probably. A toaster. A toaster is a function. Meaning what? Meaning you put stuff in, it does something to it, and it spits stuff out. That's all a function is, fundamentally. What do you put into a toaster? Bread, frozen waffles, whatever. What? Pauline, I need help. It's having problems again. What is going on? Here, let me.
I don't know.
You put in bread and you get out toast. And so for an inverse toaster, you put in toast, get out bread. It reverses the process. Jose?
Does it matter which side, like on an angle, which side you put in? I mean, like if you're trying to figure out theta, an angle.
Right.
And you're using the inverse, you're putting in the side.
What's that word? You're putting in the what? What is that word you're using? Side?
A side, side A, B, C.
Oh, no, yeah, I see what you're saying. Yeah, you're right. You could think of it as side of a triangle. You're right. We'll just deal with numbers. But you're right, it could be a side of a triangle. We'll do some things like that, I think maybe tomorrow, where we actually have a physical triangle, and we do, yeah, it is tomorrow. And we'll do exactly what you're saying. For now, they won't show us physical triangles to look at. It'll just be numbers. But yeah, tomorrow, Jose, you're right on the money. It'll be sides of triangles. Yeah. All right. So the main idea is then, inverse function switches inputs and outputs. So normal sine, cosine, tangent functions, again, you put in angles, you get out answers. So for inverse sine, you're going to put in an answer, and you're going to get out an angle, aren't you? Okay. Oh, and by the way, why I say it's bad notation, let me come back to that real quick. Do you remember, I don't know if you remember, from algebra, what does it mean if you have a number like 3 or whatever to the -1 power? Does anybody remember? What does that mean to put a -1 power on something?
1 over the number.
Good memory, Benjamin, right? Benjamin? Yeah, good memory. Yeah, it flips it. I don't know if you remember that, but it flips it. Negative powers flip. You learned back in algebra, maybe you've learned and forgotten over time. But remind you, it flips it. So if you did something like x to the -1, that's 1 over x. Negative powers flip things. Well, that's not what they mean here. Inconsistent on math's part. I want to be super clear so you don't mistake it later down the line. Normally, in every other case except functions, when you put a -1 power on a number or letter or whatever, it flips it. That's what negative powers mean. But when we put a negative power on sine, cosine, tangent, secant, cosecant, whatever, or logarithm, or f to the -1, or g, whenever you put it on a function, suddenly it takes on a new meaning. I wish math had done it differently. I wish they'd just use something new, like I for inverse or something. Because they're breaking their old rule, is what they're basically doing. -1 power means flip, but not when it's on. This does not mean 1 over sine, in other words.
There's an exception.
Yeah, they're making an exception, which doesn't make things easy. Yeah, so sine to the -1 does not mean 1 over sine, which would be cosecant, wouldn't it? It doesn't mean that. It means inverse function, switch inputs and outputs. So anyway, you just got to know that math is inconsistent there in what they came up with in their language of doing this. All right. So anyway, getting back to it. So what will really help you today is if you're super clear on an inverse trig function, you put in the answer, you get out the angle that goes with that answer. Clarence?
Should it be in radians or degrees?
They always want them in radians. Yeah, usually they're going to want them in radians. Yeah, this one's radians. So anyway, so let's do this question now. Let's do the particular question they're giving me. Sine inverse of a half. So 1/2 is what? It's the answer. And I want to find the angle that goes with it. Now, these will be on part 1 of the exam Monday, no calculator at all. So could you do this question without any calculator at all? That'll be what goes on Monday. How do we do it? Well, where are we going to go to find this?
The circle.
The circle that we love, the unit. All right, so let's put down the unit circle. Boom, there it is. All right, so I'm going to look at this unit circle. What am I looking for again? I'm looking for where sine has an answer of a half. Right, you with me? Where is sine? So look at the unit circle. Where is sine have an answer of a half? Remember, it's cosine, sine. Cosine, sine, right? Cosine, sine, etc., all the way around. Where do you see sine being, what is it? Positive, regular, a half. Right there.
And at
Also,
150.
also 150.
Ah, good eye. Cosine, sine, right there. Two answers. What's up with that? Are they both right?
No.
No. Only one of them is right. Even though they both make a sine of a half, yeah, here enters in the big painful deal of inverse trig functions. This is what causes all the trouble, makes this a fairly challenging section, and challenging for students to remember it in pre-calc and calc. When I'll be reviewing, I'm teaching pre-calc right now, I'll review in the last week of the course, so 4 weeks from now, I'll review trig with them real quickly, and they won't remember any of this, because it's really tricky what you're going to learn today. And it's specifically the restrictions. So let me talk to you now about this. Only one of these answers is acceptable. Which one is it? Now the reason why, you might wonder, why don't they accept both? Well, basically they only want, they're making it be a one, what we call a one-to-one function, meaning they only want one answer for every one input. They don't want two. They're making it that way on purpose. That way it's reversible. You see, if 1 went to 2, then when you reversed it, 2 would go to 1, and that wouldn't be a function, and it's a long story. Let me just leave it at that. They made it be 1 to 1. They only wanted one thing to go with one thing. So they said, okay, well, what are we going to do? We got two answers here. So they said, here's the way we're going to do it. We're only going to take answers in those right two quadrants for sine inverse and for tangent inverse. But for cosine inverse, we'll use these two quadrants. Isn't that weird? That's what we're going to battle with in these next 2 hours. It's getting that straight, and that is going to rear its ugly head in a million situations. The restrictions, the limits
Maybe that's where I got
on the inverse trig functions. So this is the beginning of getting that straight. So I'm going to write it out on a separate piece of paper, but so first off, sine inverse and tangent inverse, you only take answers from the first and fourth quadrants.
They overlap? Cosine?
And they overlap in the first quadrant, don't they? Good observation. Cosine inverse is just first and second. Yeah, what's the quadrant they all three share? First quadrant. They all share the first quadrant. Why? What do you remember? All students take calculus? What's true in the first quadrant? They're all positive. That's where they're all going to have their positive answers, is the first quadrant. That's why they all use the first quadrant, which means their negative answers will always be in their other usable quadrant. So for cosine inverse, you'll find his negatives in the second. When they give us a negative question in a minute for cosine inverse, we'll look in the second. When they give me a negative question for sine inverse or tangent inverse, I'll look in the fourth. Now, why did they choose those particular ones? It's because of the all students take calculus and where things are positive or negative, right? They're all positive here, so they needed one place where they could find positive answers for everybody. Students, so sine is positive in the second. They've already got positive place. They needed a negative place for cosine, so cosine's negative here, isn't it? Right? Sine is positive in the second, which means cosine is negative. So that's where they let cosine go. Do you see why they didn't have cosine go down here? All students take calculus. Cosine's positive down here.
Right.
So they didn't want cosine. There had to be two places where cosine's positive. They didn't want that. They wanted one place for cosine positive, one place where it's negative, second quadrant. And then for sine and tangent, because in the fourth quadrant, cosine's positive, that means both sine and tangent are negative, aren't they? So they have a place where sine and tangent are positive, and fourth quadrant where they're negative. They have a place where cosine's positive, everybody's positive in the first, and a place where he's negative in the second. So they have a place for positive, first quadrant for everybody, and a place for negative for all the inverse trig functions. And they really enforce this. They restrict, and your calculator knows about it, And it gives weird answers. Even using the calculator gets confusing. A lot of times when I'm teaching calculus, a couple of steps down the line, we'll do an inverse trig thing, and students go, Mr. Harron, my calculator's giving me this crazy answer, you know, and a lot of times I'll say, remember, it's the restrictions on the inverse trig. They never remember. They never remember what we're about to talk about, because it's a weird little strange point that there's these weird restrictions on the inverse trig functions. Okay, so they restrict them. Now, when I say they restrict them, they not only restrict them to those quadrants, but they restrict them to being said, stated, listed in a certain way. They want you to say negative 90 or negative pi over 2, same thing in radians, right? Oh, yeah, it's right here, huh? Oh, no, it's not. No, see how they call it 270 here, don't they? They want you to say all these angles as negative angles. Am I making any sense? Mm-hmm. Instead of calling straight down 3 pi over 2 or 270, which it is. If you start facing to the right and rotate down, that's 270 degrees, huh? But they say, no. We don't want you going through these other quadrants. Sine inverse, tangent inverse don't go there. So we want you just going up or down. And down means negative. So we're going to call that negative 90. We're going to call all this guy here, which is what? Down 30 from 360 down to 330. We're going to call him negative 30. Right here is going to be called negative 30 degrees. Not, 330 or 11 pi over 6. Actually, we'll say negative pi over 6 is what we'll say in radians. Am I making sense? They really cause some heartache with all these things. So they want these as negative on that. Ani?
Why don't they just make, or is there such thing as a unit circle just for these inverse functions?
Well, there's only one unit circle.
Yeah, but for the inverse function. You know what I'm saying?
I know what you're saying.
Yeah.
I'm not sure how else they could have done it, to tell you the truth.
To do it exactly like that, make that negative, because right now it looks like it's positive, because it is positive.
Oh, you mean, do you find one online that lists them as negative?
Is there? Yeah.
Oh, I'm sure there is. Yeah, if you want to search around on Google.
Just specifically for
Yeah, inverse. Yeah, I bet.
So
Feel free to go on Google. Type into Google.
And
Put it on your 3x5 card. Yeah, totally. Or you could just take this unit circle and write these in as negative. But there's probably something real nice, real slick.
Delete, cross out the 3 in front of 330.
She wants it clean.
No, you know what I'm saying? It's...
Right. Yeah, you could just write negative pi over 2. This would be negative pi over 6. This would be negative pi over 4. This would be negative pi over 3. That's what they are. And that's helpful. But yeah, you could probably find something real slick that shows all kinds of nice things. If you type into Google inverse trig functions unit circle or something. Probably.
What about 360? Is it just 2 pi?
It's just 0. They'll just call that 0. Yeah. Yeah, so that's how they're going to call them. Let me write those in a little bit better. I'll make the Ani unit circle here. You can market this thing, Ani. No, I'm kidding. I'm sure it's already out there in glorious colors somewhere. Anyway, yeah, so they're just going to call those by negative. It's the same locations, isn't it? You know what I mean? You could call it, it's the same spot. Right? This is 270 degrees, or it's also negative 90 or negative pi over 2. It's all the same thing. It's the same place. They just want you to call them negative angles and positive, because they only want sine inverse and tangent inverse doing the right 2 quadrants. And then for cosine inverse, they just want the top 2 quadrants. All right. So here we go back. So where were we? Oh, so the answer to our question then is just the pi over 6, huh? Even though it also exists at 5 pi, sine is also a half at 5 pi over 6. We don't include that answer. Sine inverse and tangent inverse, we just do the right 2 quadrants. So our answer is just pi over 6 right there at the half. Everybody good? So come back over here. Pi over 6. That's the angle whose sine is a half.
Inverse trig function. Unit circle. It's down.
All is well? Shall we go to number 2? That was 25 minutes for number 1. Probably better pick up the pace a little bit. No. Okay, let's try. Here's number 2. Sine inverse of negative a half. So remember, what do we plug into an inverse trig function? Is that minus a half an answer or an angle?
An answer.
That's an answer. Now, they're going to get tricky. Curveballs are coming, I'm telling you. They're coming. They're gonna stick pies in there and make it look like an angle when it's not really an angle. So be thinking. You set your mind now to follow what is true, not what something looks like. What is true is anything inside of an inverse trig function is always an answer, no matter how they try to dress it up to look like an angle, which they will do. So you set your mind in confidence as to what is true. What you plug into sine inverse is an answer. All right, so look on the unit circle. It's not too hard right now. That doesn't even look like an angle, but they'll get tricky in a minute. So there's an answer, negative half. Let's go to the unit circle and say, hey, where is sine negative half? Now, right over here, so I'm looking. Sine inverse negative a half. Now, what are the two quadrants? Sine inverse and tangent inverse are the right two, huh?
Yeah.
Now, remember, first quadrant always holds the positive answers, and the other quadrant is where you look for the negative stuff. So where am I going to look for this answer? Which quadrant?
The fourth.
The fourth. Everybody with me? I'm looking in the fourth. Because the first holds the positive stuff, and I've got a negative. So just look there for negative half. Here it is. Sine. Remember, it's cosine sine. 11 pi over 6. Oh, nope. Can't say it that way. How do we say it?
Negative pi over 6.
Negative pi over 6. Right? It's negative 30 degrees. Pi over 6 is 30, right? Because it's like 180 over 6. Remember, pi is 180. 180 over 6. That's negative 30, basically. Right? Negative pi over 6 is how they want you to say it. Right? Here it is right here. Negative pi over 6. Okay. Negative pi over 6. We're done. Good so far? It's going to get more tricky. All's well? All right. Let's try that one. Cosine inverse of negative root 2 over 2. Okay, so that's the answer, right? What we always put in is the answer. So go to the unit circle and look for that. Now is that a negative number or positive? Negative. So now cosine inverse of negative root 2 over 2. Let me put it here for us. So cosine inverse of negative root 2 over 2. Cosine inverse is those top two, huh?
Yeah.
So which quadrant am I going to look at, the first or the second?
Second.
Second, not the first, because the first is where the positive stuff always is. This is negative. So look in the second. Where do you see an end? Now remember, it's cosine sine, cosine sine, cosine sine, cosine sine, cosine sine. Where do I see cosine negative root 2 over 2?
This is
At 134.5 degrees.
135. They want the radians, 3 pi over 4.
Yeah. So it's not like made a negative number like it is for sine and tangent.
Right. No. Good question. Yeah. It's only the fourth quadrant that they call negatives.
Okay.
For whatever reason. They could have made them positive, but they decided to make them negative. Well, there's a reason, but...
so so cosine will always have a positive answer? Is that true or no?
In radians, right?
Yep, that's true. Cosines are always positive. That's right. What comes out of cosine inverse
Right.
will always be a positive angle.
Okay.
That's right. That is exactly right. So what was it? 3 pi over 4?
Yeah.
3 pi over 4. 3 pi over 4. Yeah. So even though this is negative, cosine inverse will always be a positive answer. That's right. Is that good? Is that making sense? We good on that? So all right, so we'll keep moving. We good so far? Okay. Ani's question is a good one. Yeah, so what she's saying is right. It's only the fourth quadrant where you have to say the values differently. You've got to say them as negative instead of positive. Now do you want, there is a reason. I hesitate. I don't want to confuse you too much. You don't have to know the reason. But since we're talking about it so much, here's why. They're not just trying to be mean or weird and make you do more work. There is a good reason. It has to do with the graphs, and you guys know the graphs pretty well. So let's think about the graphs for a minute. Where this all came from, this inverse trig stuff, is they were looking at the graphs, and they thought, okay, remember what the graph of sine looks like? Just goes high, low, right? The graph of sine. And they said, hey, we want to do inverses now for sine. There's the regular sine, right? And they thought, okay, we want to do inverses. But remember, we want it to be 1 to 1. We want only one x, one y, right? We don't want two answers. So they thought, okay, anytime that a horizontal line hits 2 points, do you realize that's going to be two x values that go with the same y value? Do you see that? Am I confusing you? This explanation is you don't have to know this. But here's the why they did what they did. If any horizontal line hits 2 points, that means two x values, right? These two dots have the same height, don't they? So this would be x1, x2. The two different x values. So maybe, let me give an example. This could be over at 30 degrees, and this could be at, I don't know, what's the other one? 120. If you look on the unit circle, 30 and 120 are both at a height of a half. So at 30 and 120, wait, is that right? No, 150. 30 and 150. 30 and 150 are both at a height of a half.
Right.
So that's two x values with the same y value. You know what I mean? Well, they don't want that. They want one thing for one thing. So what do they got to do? Well, you can't have a horizontal line hitting 2 points. Because if a horizontal line hits 2 points, those are two x's with the same height. So they said, okay, we're going to have to stop the thing right here. Because the minute you start going down, a horizontal line will hit 2 points, right?
Right.
So they had to stop it right there. Well, where's that? That's 90 degrees. That's the top of sine. When sine is 1, it's 90 degrees. They thought, yeah, but we need negative values. We need this is just positive. Whoop, let's erase it. This is just stuff going up. This is just positive values. We need negative values. This is the first quadrant. This is between 0 and 90. It's confusing with unit circle. Now I'm switching to the regular graph. This is positive values. They thought we need the negative values. Where are we going to get negative? Well, sine goes negative here. Down here it goes negative. Yeah, but we'd have to skip that whole section. Well, this gets to 180 and then take it from 180 to 270. And that would be weird, skipping a section in the middle to pick up the negative values down here. So they said, what can we do? We could go back here to negative 90. And we'll get the negative values for sine, and that'll be in one fell swoop. From negative 90 to positive 90. Negative values, positive values. And no further. Don't let it come up, because then a horizontal line will hit 2 points. Right? You can't have a horizontal line hitting 2 points, or you'll be wrecking the 2 for 1 thing. We want 1 for 1. So they stopped it right there. They stopped it right there. That covers the full range of negative values to positive values, and it's all in one connected piece, instead of taking this and then this piece way over here. That would have been the big numbers, the positive numbers that we're used to. So you see, that's why they went negative to positive. They were just looking at the original graph. All right, so whether you tracked with all that or not, that's why and cosine, why didn't they have to do that with cosine? Tangent, same thing. You know tangent, right? We did him yesterday. Right? Remember, where's he go? Negative pi over 2, what's that? Negative 90, positive 90, what does he do? Snake, he covers all his values between negative 90 and positive 90.
So the inverse of sine is tangent?
No.
No?
Oh, it looks like tangent, though. They look a lot alike. The curvature is just a little different. But they're both kind of snaky, aren't they? Yeah, they look very similar.
They're backwards.
Yeah, the bending is backwards. Well said. This is, well, you know what this is? This is concave down.
Yeah.
So when you go into calculus, you talk more about concavity. This is like a bowl turned down. See how this is a bowl turned up? Concave up? Yeah, that's what you mean by backwards. The technical word is concavity. Yeah, and the bend is down, this bend is up. Yeah, right, opposite concavity. Yeah. So you talk more about that in calculus. It's called the second derivative determines concavity. Anyway, so that's why, see why they did tangent and sine, negative 90 to positive 90? Covers all the values. And then for cosine, now think about cosine. Why they did cosine differently. What does cosine do? He starts high, doesn't he? Goes low and goes here. There's all his values right there. You don't need to go anywhere else. From 0 to 180. Cosine covers high to low. So they just took him 0 to 180. That's the first two quadrants, isn't it? And they go, boom, we got all the values for cosine. Don't let him start to go down, or 2 points. Don't let him start to come up, or horizontal line hits 2 points. We don't want that 2 for 1 thing. That's what they did. So that's where it all came from. It's okay if you didn't track with all that, but that's the reason. So that's why we have our restrictions as chosen for sine, cosine, tangent, inverse. All right, let's get back to it. All right, so next one. Now, this is going to be a little harder because we're no longer on sine or cosine. We're on tangent, which means it's not directly on the unit circle. It's there, but you got to kind of piece things together on the unit circle. What do I mean? So I'm going to go to the unit circle, and I'm going to say, remember, this is the answer. I'm looking for the angle. It equals some angle. Keep that in mind. That's the most fundamental truth of inverse trig functions or any inverse function. We plug in the answer, we get out the angle. So I'm going to go to the unit circle now, and I'm going to look, say, hey, what angle has tangent root 3 over 3. Which quadrant am I going to look in? Is that a positive or negative?
Positive.
It's a positive answer. So I'm looking at which quadrant? First only. Don't even need to go outside the first. So let's go to the first quadrant. So I'm looking right here, right? Tangent inverse is first and fourth, right? Tangent inverse is first and fourth. But I'm not going to the fourth because it's positive. So I'm up here, positive, in the first quadrant where they're all positive. Okay, so now what am I looking for? I want to know where is tangent root 3 over 3. So tangent inverse. Now, this is cosine sine, cosine sine, cosine sine, cosine sine, cosine sine. It's not tangent.
But tangent is sine over cosine.
Yeah, so this is where you need to remember that. Do you remember? Sounds like you do. Tangent is made out of sine over cosine. Remember, sine and cosine is everything. All the other 4 trig functions are just made out of sine and cosine, aren't they? They're all Johnny-come-latelys. Sine and cosine are the originals. They make everything else. All of trig is really sine and cosine. So, if I want to find where tangent is root 3 over 3, I got to somehow find a spot. It's going to be one of these 5 locations. And really, it's going to be one of those 3 in the middle. One of those 3 locations in the middle of the first quadrant, where sine over cosine will end up being root 3 over 3. Can you tell where that's going to happen? You just guess, and then try it out. If it doesn't work, try another one.
Well, I'm thinking it's got to be either 30 or 60 because it was the only ones with
Yeah,
reason.
good thinking. It can't be the 45 because that doesn't even have a root 3, huh? That's just got the root 2 stuff. So it's either 30 or 60. Let's do it wrong at first because I want to show you how to be wrong. The wrong answer is 30. So let's try 30, I think, if I'm thinking right. So, oh no, that's the right answer. That's actually, I just realized now that I started to think about doing it, that's the right answer. Anyway, let's just do it. So, sine over cosine. Sine's a half over cosine, root 3 over 2. So for this one, right? For pi over 6, 30 degrees. Sine over cosine. Good so far? Now, how would you simplify that? Now, we'll first cancel those 2's out. Yeah. Then we have 1 over root 3, and then we got to get the root in the top. What's going to get the root in the top? Top root 3. What's the answer? Root 3 over 3. See? Boom. That's the one we're looking for. That's our spot. Everybody see that? It is pi over 6. The sine over the cosine there the tangent does become root 3 over 3. Answer's pi over 6. That's our angle where the tangent becomes root 3 over 3. Good? So you just got to guess around at those. So pi over 6, right? Pi over 6. Is that okay? Do you want to talk about that anymore? Does everybody see that? You could have tried the 60, and it would turn out upside down. Doesn't quite work. So you just got to guess, sine over cosine. You knew it was one of those. You knew it was either 30 or 60, because those are the only 2 in the first quadrant that have root 3's in them, huh? So it had to be either 30 or 60. So just try one. If it's not that one, it's the other one. All right. All right, you want to try that one? Tangent inverse root 3. In fact, I'm just going to go to the unit circle, because it's all about the unit circle. All right, so which quadrant are we looking in? It's positive, so we're always looking in the first quadrant for any of these trig functions when they're positive. First quadrant, tangent inverse of root 3. So you're thinking, oh, that's sine over cosine, because that's what tangent is. You get comfortable with that definition where you just know it off the top of your head? Tangent is sine over cosine. So where will sine over cosine be root 3? Again, it's got to be 30 or 60, doesn't it? Those are the only 2 in the first quadrant that have root 3's in them. And we just did the 31 last time, and we saw it wasn't root 3. It's got to be the 60. Let's prove it. It is the 60. It is pi over 3. Let's prove it. What do you get for sine? You get something. For sine, what is sine? It's cosine sine. Sine you get root 3 over 2. Cosine you get a half. Everybody good there? Sine over cosine? And then you know how to simplify that. Cancel the 2's. Get root 3 over 1, which is just root 3. That's it. It is pi over 3. Is comfortable? So the answer is root 3. No, pi over 3. There it is. All right. All right. Hit the buttons on the calculator. Make sure you're in the right mode. Radian, sine inverse, negative 0.73. I'm getting the answer. Negative 0.82, 818, 82. Y'all getting that? Is that working out? Can I help with that? We all good? All right. I'm going to move on. Grab me at the break if you're not able to get these kind of calculator things. Each calculator is a little different, so. All right, so try that. Cosine inverse. Root 2 over 8. Again, make sure you're in radian mode. $1.39? We good? Questions on that one? All is well? All right, grab me. Okay, sine inverse of sine of pi over 5. Where did that?
My calculator, it's in radian mode and everything, but it's just giving me.
So, what now we're putting two of them together. Now the fun starts. They'll cancel each other out?
Yeah.
What makes you think that, Clarence?
Inverse sign and negative sign, it's like this one, this one.
Perfect. I like the way you're thinking. You're thinking very well. That's right. That's right. They're opposites, right? Just like a toaster and an inverse toaster. If you do them both, they cancel each other out. They're opposites, huh? Totally right thinking. Is everybody seeing that?
In the tutoring center thingy?
Yeah, no, I know there's other stuff. We'll get there. But let's start with this fundamental thought. They cancel each other out. Right? They cancel each other out. They are opposites of each other. And that is a great thought to think as you're moving into higher math as well. Pre-calc, calc, we use that idea all the time. I'm teaching pre-calc the hour before your class, or the 2.5 hours before your class this summer, teaching pre-calc, and we just talk a ton about inverse functions, not just trig ones, but all kinds of them, because that's what you use to cancel stuff out. You use them all the time. You probably just don't even realize it. Think for a second, like if you were to solve x squared equals 9, how do you solve x squared equals 9? How do you make that into a regular x? What do you do to get rid of that 2? You root it, huh? You come in and you go root. Well, you know what the root is? It's the inverse of a 2 power. Right? What do you do if you have a root? What if it starts with a root? Square root of x equals, 4 or whatever. What do you do in that case to get rid of that root? You 2 power it, huh? Because the 2 power gets rid of the root. So the point is a 2 power and a root are inverse functions of each other. They undo each other. They're like a poison and an antidote. They eliminate each other. So that's an important concept as you move into higher math. We have functions and inverses. Yeah.
So which is the dominant? What's it going to become?
Oh, so in other words, yeah, good question. These are going to eliminate each other out, and the answer is just pi over 5. Boom. Going to be your favorite question in the next test, right? They just eliminate each other out. Pi over 5, they're opposites. Just like if you have the square root of 7 and you put a 2 power on it. They cancel each other out, and it's just 7. Get that idea? A 2 power and a root are inverses, just like a sine inverse and a sine are. They just cancel each other out. Answer is pi over 5. What could be easier? So here's number 10. Yeah. Tangent of tangent inverse of 4. What do you think?
4.
Yeah. right? They're inverses. Boom, boom. Answer is 4. Like I said, you want a lot of these on the next test, right?
Yeah, the whole test.
Right? They're just opposites. They just can't. It's just like, Benjamin's analogy, it's like saying I did the inverse toaster of the toaster and I put in bread. Right? Think about what happened. You put bread into the toaster and make it into toast, and then into the inverse toaster, what would it be in the end? Back to bread. See how these guys cancel each other out and it's just bread? That's essentially what we're doing, right? Bread goes into the toaster, comes out toast, put it in the inverse toaster, changes it back to come out bread. So these cancel each other out. It's back the way it started. If you take that bread and you run it through both the toaster and the inverse toaster, it's back the way it started. So that you take this 4 and you run it through tangent, inverse, and tangent, it's back the way it started. Same thing, huh? Inverse functions cancel each other out. Clarence?
It didn't work out in my calculator.
It didn't work out in your calculator. Tangent of tangent inverse of 4?
Yeah, man. I did inverse tangent.
Maybe the calculator's broken. No. All right. Questions? You want like 10 of them to be these things?
Yes.
All right.
That one is not 3 pi over.
What's the answer? They just cancel each other out, right? Just 3 pi over 4. What could be easier? This all. So here it is again. Now, this does not equal 3 pi over 4. You can't just cancel it on this one. Why? Because 3 pi over 4 is not in the tangent inverse zone. And what's the tangent inverse zone? Negative pi over 2 to positive pi over 2. Remember that? 3 pi over 4 is not in that zone. Is it not? Let's change it to degrees. I think we'll see it much more clearly if we change it to degrees. So if you stick in a 180 right there for pi, then what is that? That's 3 times 180 over 4. Is it 135? Yeah, it's 100. So this is 135 degrees. 3 pi over 4. It's 135. What's the zone? What's negative pi over 2? Negative 90 degrees, because pi is 180 again, right? Pi is 180. Negative 90 to positive 90. That's the zone for tangent inverse and sine inverse, right? So is 135 between negative 90 and positive 90? No. It's not in the zone. You see, these other ones were. The reason it worked so well right here, well, that's a different story. I'll get to that in a minute. Pi over 5, yeah, that's 180 over 5. What's that? 36 degrees. That's in the zone. That's between negative 90 and positive 90, isn't it? So yeah, just boom. If they're in the zone, boom. Those are easy. Just cancel them out. But if they're not in the zone, you can't do that. Well, then what do? You work it out longhand from inside to outside. What do I mean? Take this first and just do this. Just do tangent 3 pi over 4. Go to the unit circle. Let's just take 3 pi over 4. Let's just start on the, like, parentheses, right? You always start with the parentheses, right? Starting on the inside. Do tangent 3 pi over 4. Let's go to the unit circle here. Okay, where's 3 pi over 4? There it is. Cosine, sine. So tangent 3 pi over. Tangent is what over what? Sine over cosine. Sine over cosine. So it's root 2 over 2, sine, over cosine, negative. So there's cosine and sine, right? Root 2 over 2 over negative root 2 over 2. What's that? Notice that's the same thing over itself with a negative sign. That's negative 1, right? Whenever you divide the same thing over itself, it's a 1, right? But it's negative, so negative 1. We good to there so far? So that's negative 1. So what? So that means the tangent of 3 pi over 4 is negative 1. You have to do all this without a calculator on Monday using the unit circle. So tangent of 3 pi over 4 is negative 1. So that means the inside is negative 1. Let's go back. That means this inside is negative 1, isn't it? Good so far? So when you can't just cancel them because they're not in the zone, you just do inside first, negative 1. So this question becomes, that's negative 1. So this question becomes now tangent inverse of negative 1. Good so far? The whole inside I did first. The whole inside became negative 1. And now, do tangent inverse of negative 1. You ready? Where am I going to look? I'm going to go to the unit circle again to find the answer to this. Which quadrant am I going to look in for tangent inverse of negative 1? Now I'm going to do tangent inverse. Remember that tangent inverse is the right two quadrants, right? Negative 90 to positive 90? And it's a negative number. Where do you find the negative ones? Fourth quadrant. Not the first. First everything's positive. Fourth quadrant, huh? Fourth quadrant. We good? Okay. Tangent is sine over cosine. How can you get sine and cosine coming out to be 1 or negative 1 or whatever? They got to be the same. The only way you're going to divide two things and get an answer of 1 is if those two things are the same. Right? You with me? So I'm looking here. I'm saying, okay, cosine sine, cosine sine, cosine sine. These are the same. Cosine sine, cosine sine. See how these are the same? Except one's negative, one's positive? That's my spot. They're the same there. One's negative, one's positive, so they'll be 1 when you divide them. Negative 1 because one of them's negative. That's my spot. What is it? 7 pi over 4, but so many wrinkles. One more small curveball. You can't say 7 pi over 4. Yeah, you got to say negative pi over 4. It's the same place, but you got to say it their way. Negative pi over 4. That's our answer. Negative pi over 4.
Now, Wendy was saying in the tutoring center that if you just follow that diet.
Yeah, nice. I like the way Wendy's saying. If you just take this spot and shoot back into your permitted quadrant, you'll find it. That's true. That's a nice way to do it. Yeah, the original question they gave us. So it's kind of like they sort of cancel out. How's that? They sort of cancel out reflected back into the correct quadrant. That's the real truth. That's probably what Wendy was teaching. Good. See, that's why I picked Wendy. She really gets it.
It's just
Yeah.
a flip on that axis.
Yeah, that's what it is. So yeah, there's another way. I don't know if you want 27 ways. I'm maybe confusing you more. But that is true. When I say, hey, these don't cancel, right, but they sort of cancel. No, like, what's the reason they don't, what am I saying, sort of cancel? Well, they don't cancel because he's not in the zone. So they cancel, yeah, but they throw him back in the zone. That's what they do. So how do you throw 3 pi over 4 back in the zone? You reflect it. 3 pi over 4 reflects, right? You reflect through the origin. That's where our answer ended up, huh? It basically throws it back in the zone, is what it does. They cancel back in the zone. Yeah, that's another way you could do it.
Wait, so
Honey.
that thing that Helen just said, that we could use that for all these problems now?
Yeah, that'll work.
For sine and tangent.
For
Or cosine.
Or will cosine.
It'll throw it back in the zone. That always works.
and
Yeah.
these are only for the
I'm not sure that's easier. I'm not sure I'd rely upon that. I mean, it might be I don't really want to teach two ways. I'm going to confuse everybody. That's what I did when I was first a brand new teacher. I thought that'd be helpful. My first couple years teaching, I thought, I'll just show them like 3 ways to do every problem, and they can pick their favorite. I confused everybody. And I learned soon that students like one way over and over and over and over again until they can really get the hang of it, rather than 3 ways.
I'm a very visual person, so I like.
Yeah, if you really, so I'll just say it once. If you really like that, see me at the break. I can help you more with that. But otherwise, I'm just going to go back to the regular. I think that'd be more helpful to the big group.
Work it out.
All right. So let's try this one. So sine of sine inverse of pi. Oh, that's such a tricky question. Yeah, is that the next question?
Yeah.
What was number 11? They really, I wish they would ease in a little bit. Let me see. All right, so then, how do we do this problem? So what you want to ask yourself is that in the zone?
Yeah, it's inverse 60. Inverse sine, it'll be 360, right?
What's that?
It'll be 360 since inverse sine. If it was like a regular sine, it'd be on the other side, right? Or
Oh, you're trying to do that reflection trick?
yeah.
You like that trick, huh?
Yeah.
Okay, it's not going to work here. There's a more fundamental question to ask ourselves, rather than, is it in the zone or whatever? And that is this. Is that an angle? Or is that an answer?
Oh, that's right. 'Cause
And don't go by appearances. Here comes the big curveball, knuckleball, slider, whatever. They are really throwing us the junk pitch here. The only way you're going to be able to handle this junk pitch is if you are crystal clear on whether something is an answer or an angle, and it has nothing to do with how it looks. Don't look at it and go, well, pi, that's always 180, that's an angle. No, pi's a number. Pi can be 3.14. If it's a number, it's 3.14. If it's an angle, it's 180. So it can go either way, right? Pi can be either one. So they're trying to fool you. They put a pi there because they want to fool you. They're trying to throw the junk pitch. They're trying to fool you with that pi thing. How you not be fooled is remember how we started today with. What was the first thing I did is I said, a regular sine or cosine or tangent, whatever, what do you put in? Angles. Like pi over 6 or 30 degrees, and you get out answers like a half or whatever, right? Regular trig functions, you plug in angles. Inverse trig functions, you plug in answers. And you get out angles. It reverses it, huh? So you got to look at so it has nothing to do with how it looks. Don't worry about how that looks. But look at what it's being plugged immediately into. Look at its context. Look what's around it. Don't be fooled by looks. Look at what is immediately around it, its context.
So because it's the inverse sine,
It's being put into inverse sine, yeah. So we have more sine, that's later. Right now it's being put into immediately. Now it's being put into inverse sine. What do you put into inverse sines?
The answer.
Answers, not angles. So in other words, this here, this pi, is a number. 3.14. It's an answer, not an angle. That's not 180. Why? Because of where it sits. It's all about where it sits. If it's being put into sine inverse, or any inverse, it's an answer. We put answers, right? It's like we don't put bread into our de-toaster, or our inverse toaster. You put in toast, and it turns it back into bread.
It comes out to
Right? I don't know what it would do. Yeah. So, yeah. So, right? Is everybody clear on that? You got it. The only way to know is by context. Like what's around it, what's it being put into, not the way it looks. They can really fool you if you're paying attention to looks too much. It's what is being put. It's being put into sine inverse, and that means it's an answer. Okay, so what? So we got that straight. So this is an answer. This is a number, not an angle. So I'm not thinking anything about the negative 90, positive 90. It's not an angle. I'm not thinking about those restrictions on the unit circle at all, because that's not an angle. You with me? That's a number. Well, then what am I thinking about? Well, okay. That's an answer, isn't it? That's an answer that comes out of sine. Meaning, there's some angle, and the answer came out to be pi, 3.14. You with me? That's the answer that came out of some angle. Let's go look at the unit circle and see what the answers look like for sine. So let's see. Remember what pi is again? 3.14. So just think about 3. Right? Good enough. About 3. Let's go look. So as we look at the unit circle now, let's look. We can look anywhere we want. Cosine, sine. There's an answer. Half. Remember what we're looking for?
3.
Pi. We're looking for an answer that's pi, which is 3.14, about 3. There's an answer, a half. That's a lot smaller than 3. Cosine, sine. There's an answer. Now, root 2 over 2, if you have your calculator, that's 0.7 something. Cosine, sine. Root 3 over 2, that's 0.86, I think. Cosine, sine. Hey, there's sine. 1. That's the biggest sine we've had so far, huh? 1. Cosine, sine. There's root 3 over 2 again. That's 0.86. Cosine, sine. There's that 0.7 number. Cosine, sine. There's a half. Cosine, sine. Sine's a 0 there. Now these are all negative. What's the biggest answer you see for sine up there? 1. Yeah, because that's the highest point. Remember, sine is your height, your y value. That's for sure the biggest sine up there. So what's the biggest thing, what's the biggest answer you can ever get out of sine? 1. You're never going to get 3.14. This is a silly question. No answer. Do you see that?
None of the above.
None of the above, or whatever that other bubble is, that second bubble. Do you see how I figured that out? You're never going to get the answer bigger than 1 out of a sine. Remember when we graphed sine yesterday? Or 2 days ago? Right? Remember sine starts 0, goes up, goes down. How high does he go? For regular sine, with nothing, with an invisible 1 in the front. Goes up to 1, down to -1, huh? The highest sine ever gets is 1. Unless you put some other number in the front. We're talking about regular sine, no number in the front. The highest he ever gets is 1. The lowest he ever gets is -1. That's what we see on the unit circle. Here's his lowest value, -1, right there, cosine sine. Right? You can't get up to 3. You can't have an answer coming out of sine that's bigger than 1. No way. So you go back here and you go, oh, they're trying to fool me. They're giving me an answer coming out of sine that's bigger than 1. That's not possible. Undefined. That make sense, Clarence?
So in a brief overview, for the inverse sine, when it gave you the answers, you determined the answer within the whole inverse sine, and then from there, since the sine, regular sine is outside of that, you're going to try to find that answer on the unit circle. That's essentially what you're doing each time we do this.
I never even got to this at all. I just looked at sine inverse of pi, and it was no way right there. So my problem was with sine inverse of pi. I never even went further. You can't do sine inverse of pi. Try it in your calculator. You can hit sine inverse of pi. Make sure you're in, no, it doesn't matter what mode you're in. Just hit sine inverse of pi. Either mode. Yeah, it doesn't. Why? Because that's not an angle. Right? Doesn't matter if you're radians or degrees. It doesn't matter. Hit sine inverse of pi, it'll go air. Did you get it?
What if it would have been 1 or less?
Then we would have had to do it longhand, the way we did the last one. So yeah, so let me write, I know this is kind of confusing, huh? Let me write out, now that we've seen all the cases, let me write it all out neat and clean, hopefully. Some neatness and cleanness to it. So here's the deal. If I can summarize it. If you have sine inverse of sine of x, or cosine inverse of cosine of x, or tangent inverse of tangent of x, all of those just equal x when, not wex, when x is in the zone. So the first thing is they just cancel when x is in the zone. And what is the zone? You know, sine inverse and tangent inverse, the minus pi over 2 to positive pi over 2, and cosine inverse 0 to pi. So that's the first thing. But there's more to the story, as we've seen. So first off, those three just equal x when x is in the zone. Actually, let me change it up a little bit. Come down here, I'll say when x again, when x not in the zone, when x is not in the zone, work it out starting on the inside. So that's what we did with the tangent problem. Good so far? So those are the first two problems we did. So if the x is in the zone, whatever the zone is for tan inverse. Oh, and why? Why? Because this is an angle. This is an angle, and this is an angle. How do I know? How do I know that? It's just x. It's not even a number or degrees. How do I know that's an angle? Because of where it sits. Because of its context. It's being put into tangent or sine or cosine. It's being put into a regular trig function. What do you put into a regular trig function?
Angle.
You put in angles. And you get out answers. Huh. So in that case, in those three cases there, x is always an angle. So if we're talking about an angle, then we think about the zone, the angle zone. And if you're in the zone, it's just x. And when you're not in the zone, you work it out other way. Now comes the trickier case when they reverse all that. And they say, okay, now what if we do sine of sine inverse of x? Or tangent, well here, got a special wrinkle here. Or cosine of cosine inverse of x. Do those just equal x? Yes, when x is -1 to +1. Because in this case, this x and that x are answers, aren't they? And the answers to sine and cosine have to be between -1 and +1. So this is the trick. There's zones for everything. There's zones for angles and there's zones for answers. And you got to know whether you're dealing with an angle or an answer. And how do you know that? Where it sits. It's context. I'm going to do tangent. Tangent's a special case. Is that what you wanted? Another special case? One more.
Because it goes from.
It's always good. So, does everybody see this first off? Everybody see what I'm saying? See how the order is reversed? Do you see why this, in the second case, this x is an answer? Because of where it sits. It's being put into inverse trig functions. So it's an answer. So when it's an answer, the answers for sine and cosine have to be between -1 and +1. So as long as they are, that's a yes. And then if x is not -1 to +1, then it's no solution. So if x is not between -1 to +1, it's no solution for those two. You just can't do it.
So all you got to do is look at the number.
All you got to do is look at the number. So that's why they give me pi, right? They give me pi, that's 3. That's not between -1 and +1. No solution. Everybody see what I'm saying there? So what have we done? So let me fit in here the problems we've just done and see how they fit for this. I'll come back to this. Let me just flash back real quick. So what have we solved so far? We started with this. Sine inverse of sine of pi over 5. What was it? What number was that? Number 9. So we did sine inverse of sine of pi over 5. Question number 9. Do you see that? First off, that pi over 5 is an angle. Again, I'm not saying that because there's a pi there. Don't let the looks fool you. I'm saying that because of where he sits. He's being put into sine. He must be an angle. So if he's an angle, I think about the angle restrictions, and I say sine inverse, is he between -pi/2 and +pi/2? Yeah, if you put 360 in there, 360 over 5 is, I don't know, when is it? 72? I think it's 72 degrees. Yeah, 72 degrees. Yeah, that's between -90 and +90, isn't it? So that's why they just canceled, and the answer was just pi over 5.
What's the problem with my number 12?
Just a second, let me go through the ones we've done. That's why that happened in number 9 now. Do you see? Because it was this type, it was an angle, because it's being put into a regular trig function. And so you say, oh, if it's an angle, ask if it's in the zone, -90 to +90. Yeah, it's 72. Pi over 5. I'm supposed to do 360. Why am I doing 360? You guys just got to say something when I go crazy like that. It's 180. Isn't that?
36.
Thanks. 30, it's 30, still in the zone, but 36 degrees. 36 degrees. Anyways, pi is 180, right? 180 over 5. Were you thinking, now what is he changing pi? Did pi change? Pi is still 180. So, right, so that's in the zone, pi over 5. Now, and then came like number 10. What was number 10? Was it this one? Yeah. Look at that one. Tan inverse 4. Tan inverse. So number 10 is down here. Actually, I haven't described number 10 to you. Tan inverse of x just equals x. Right? Number 10 that we did said tan of tan inverse of 4. Is that 4 an answer or an angle? Okay, don't look at the looks. Doesn't have to have a pi or not a pi. Or don't go over that. Just look at where it sits.
It's an answer.
Being put into tan inverse, it's an answer. Right? You put angles into regular trig functions, answers into inverse. So that's an answer. So then what? Should I say, hey, is the answer -1 to +1? No. That's for sine and cosine. For tangent inverse, it's always. Why? Why is tangent inverse not limited like the answers for sine inverse and cosine inverse, right? See what I'm saying up here? If the answers, and this is answer also, answer right there, they're all answers. So why does tangent, always? Yeah, always. Because remember the answers remember the graph for sine and cosine. Sine goes like this, high 1, low -1. Cosine basically does the same thing, just shifted. But what is tangent? We did it yesterday. He's a snaky. He goes as low as you want and as high as you want forever. Remember the tangent graph covers all heights and all depths. All answers are fine with tangent. Lot to remember, huh? It's a lot of little... What are they doing there? What's going on there? How's this different than the last problem? The last 9 problems?
They're not inverses of each other. They're different.
They're mixing the functions. Now it's not sine, sine inverse, cosine, cosine inverse, tangent, tangent inverse. It's tangent, cosine inverse. They're mixing them. This is what you were hoping for? I hope they mix them. What happens when they mix them? All right, you guys are looking a little tired. Maybe we better... All right, let's push on to the end here. We got to finish this section. I'd like to start the next section at least. We're supposed to do half of it today, the schedule says, and half of the next section. So let's finish this up, and we'll start the next section. Okay, so what the deal is here is they're mixing the trig functions. So that's a lot of the battle in a math test. Have you ever taken a math test where you sit down, you get the test, you look at it, and you kind of feel like they all sort of look alike? How do I know what to do where? That's a lot of the battle is identification. So let me help you with that. The exam we'll take next Monday. You'll recognize this by the fact that they're mixing the different ones, huh? Everything we've done up to now has been sine, sine inverse, cosine, cosine inverse, tangent, tangent inverse, right? The same function twice. By the way, from the question that was being asked at the break, I want to make sure, did we all catch the difference between the top section and the bottom? The -1 has moved. I don't know if I said that very, very clearly. Are we all clear on that? Manveer was asking me about that, so that's a good question. Does everybody see that? See how the -1s are on the outside and the red ones? And on the purple ones, the negative ones are on the inside? That's a big difference. That is the difference. Did everybody catch that? That's why I have this wall of separation here. So this is this and this. And then the purple goes with the purple. Everybody see that? See how it's really important whether the inverses are inside the parentheses, whether the inverses are outside the parentheses. It makes a big difference because that changes whether the x is an angle when it's in regular sine, cosine, tangent, or it's an answer if it's in an inverse. And that changes everything. We good on that? Everybody saw that distinction? Okay. So with that in mind, let's get back to this one. So how do we do this one? So what you want to recognize on the exam is they're mixing them here. It's not the same thing twice. It's a mix. And what do you got to do for that? Draw a triangle. So you want to just kind of know in your mind, oh, there'll definitely be one of these on the next exam. When you see this thing, you think, oh, I've got to draw triangles. Okay, how so? Well, this is positive, isn't it? So I'm just going to go to the first quadrant, and I'm going to draw a triangle. This is going to be very similar to the triangles we did, what was it, 2 days ago? Something like that. I'm going to draw one of those triangles. All right, so here we go. Let's start with, is 15/17 is that an answer or an angle? Look at where it sits. It's being put into cosine inverse, so it is an answer, huh? Right? So that means that there's some angle. 15/17 is the answer, right? 15/17 is what the cosine of some angle equals. Everybody good with that? Do you see what I'm saying there? Right? 15/17 is an answer, meaning the cosine of some angle is 15/17. I don't know what that angle is, but are we good so far? In fact, that's what cosine inverse means, right? You put in an answer, you get out an angle. That's all trig functions. Inverse trig functions. Inverse trig functions. You put in an answer, you get out an angle. Don't you? So this cosine inverse, what will come out of this thing is an angle, call it theta. Just making up a name. That's what we usually use for the Greek, for angles. All right, so I'm going to put that theta where we always put theta when we make the triangles, and I'm going to do what we learned about Sohcahtoa. Sohcahtoa. This is cosine. Cosine is what? Adjacent over hypotenuse, huh? So here's theta. This is the hypotenuse. This is the adjacent side. That's the opposite side. So cosine is adjacent over hypotenuse. 15 over 17. Good so far? Just like we did before. How do we find that other side? Pythag? Yeah. So 15 squared plus b squared is c squared, right? A squared plus b squared is c squared. The c is always the hypotenuse, isn't it? You good there? So 15 squared, what's that? 225 plus b squared is 289. Subtract 225. B squared is, what's that? 64. That's nice. Root it. B is 8. So that other side's 8, huh? Everybody good to there? Let me pause for a second. Everybody see how I got here? I said, oh, it's a mix of trig functions. You just know, got to draw triangles. So when you get this on the exam on Monday, when they mix the trig functions, you think, got to draw triangles. Put it on there, put theta, and cosine inverse, 15/17 is the answer, right, for an angle. Put that angle in there, do the triangle thing. Now, we're like one step from the answer. How so? Now you go to the outside. The inside's done. Now go to the outside. It's tangent. And what does the inside become? What is the inside right here? Theta. The inside's just theta. remember, you put an answer into cosine inverse, out comes an angle. Right? That's what we always do with inverse trig functions. From the start of today, an hour and a half ago, we put answers in an inverse trig function, out comes an angle, huh? So that means the 15/17 is going into this toaster, or inverse toaster, and out will come an angle. So then this is tangent of theta then. That whole inside is just theta. It's just the angle that came out of cosine inverse.
But we needed to solve it because we needed...
Yeah, we needed to use that angle to find everything out about the triangle, but now that we got everything about the triangle, now we can finish up. Tangent of that angle. Look at the triangle. What's tangent? Toa? Yeah, opposite over adjacent. What is that? Opposite, adjacent. 8/15. Done. Just like that. See how we used the triangles? Very much like last time, huh? 2 days ago, whenever that was. Was it last week? Yeah. Clarence. What's that?
No, I was thinking that so we don't have to like somehow find out the unit circle. That's it.
That's it. Yeah, no unit circles on these. Just drawing the triangles. That's right. Just drawing the triangles. We good? Other questions on that? Want to try one of those? This one is negative. Let's go back. So this one was positive. 15/17 was positive. So I drew my triangle in the first quadrant. But this one is negative. So when I draw my triangle, right? When they're mixing the trig functions, you always draw a triangle. No unit circle at all. Just draw the triangle. When they give me a negative one, I've got to go where cosine's negative.
Which is
Where's cosine? Remember the restrictions?
second
Cosine inverse. We're talking cosine inverse here. So we're thinking about restrictions, huh? First and second quadrant is all we use for cosine inverse. Sine and tangent inverse use the right two quadrants, first and fourth. Cosine inverse uses first and second. So negative values, where am I going?
the second.
Second quadrant, not the first, huh? Because the first is where everything's positive. So we're going to the second quadrant.
I thought you said all cosine was positive.
All of his angles are positive, but this is an answer. All of his angles are positive. 0 to 180, all positive angles. But his answers can be positive or negative. What comes out of it. All right, so go ahead and try it from there. Just want to make sure you had that part straight. So you know where to put your theta, right? Always goes at the origin. Take it from there. Use the Sohcahtoa. See if you can get the whole triangle and finish the problem from there.
I like you using X and R better instead of XR.
Oh, yeah, we got to use Sohcahtoa here. So Sohcahtoa. Okay, so this inside part is cosine inverse, right? That means there's some angle whose cosine is negative a half. You tracking with me? There's some angle whose cosine is negative a half. Right, everybody see that? So put that on. Oh, and by the way, if you want to just forget about the negative, you can just forget it. You can do the signs at the end. You can figure out what the sign should be, positive or negative and all that. At the end, just based on what quadrant you're in, all students take calculus. Remember that? That's how my daughters, when I was doing Trig and pre-calc with them a couple years ago, that's what they did. So if it's too confusing to worry about the negatives along the way, that's fine. You can just do them at the end. Clarence?
For that specific one, how did you know it was gonna be the second quadrant for that one?
Yeah, because cosine, the answer came out negative. So remember, the restrictions for cosine are the first two quadrants for cosine inverse. It's the first two quadrants, and it's not the first because that's where everything's positive. So it had to be the second. That makes sense? Yeah, so we're still dealing with those restrictions, aren't we? See how I said it just shows up in a million places. So the cosine inverse restrictions are first or second.
So when we get our answer, since it's going to be in sine, which is the second quadrant, it'll be positive.
Exactly. Well said. It's going to be sine, second quadrant, all students, sine is positive. Yeah, so we know our answer is positive, don't we? Exactly right. So cosine is adjacent over hypotenuse, right? Hypotenuse, adjacent, opposite. And so this is 1, and hypotenuse is 2. So look, I'll just skip the signs. I'll just put regular 1, regular 2. Who cares about the negative? I can fix all that later if you want. Just put the 1 and the 2. And now do the Pythag to find the other and the other side. A squared plus b squared is c squared. So that is a squared plus 1 squared is 2 squared. A squared plus 1 is 4. Subtract 1. A squared is 3. So a is root 3. So this side is root 3. Good to there? So we got the whole triangle. Now, what are we going to do with the triangle? Well, the final question is sine. We go to the outside, right? This inside is all theta, isn't it? Why? Because that's what comes out of an inverse trig function. You put in an answer, you get out theta. So this is sine of theta. Really. Right? The whole cosine inverse becomes theta. Why? Because that's what always happens with inverse trig functions, right? From the beginning today. Inverse trig function, you put in an answer, you get out an angle. I'm just calling it theta now because I don't know what it is. Right? So that whole inverse trig function becomes theta. But it helped me create the triangle. So that now I can take sine of theta. What's sine? Opposite over hypotenuse. So root 3 over 2, huh? And now I can decide if it's positive or negative. This is how my daughters always wanted to do it because they didn't want to worry about the pluses and minuses along the way. So at the very end, they would just do the all students take calculus. They loved that. All students take calculus. All are positive, sine is positive. This is sine, he's positive, done. Don't even need to worry about the signs. Now, if you wanted to be careful with the signs along the way, you don't have to, then it's just all about back 1, up 3, isn't it? Back 1, up 3. So that's why it's positive root 3 over 2, because it's positive.
So does that affect it even though you said that the angles are positive for cosine?
Yeah, the angles are positive.
So even if there was a negative in the problem, because we're
Answers can be negative.
Oh, it can?
Yeah.
Even if it's cosine?
Yep. I know it's confusing with the angles and the answers. You want to really try to get the difference straight, whether something's an answer or something's an angle. That'll really help make a lot of sense out of what we're doing here. Is that good on that? Is that okay? We're going to do this with x's in a minute. So you want to be comfortable with the numbers. There's always more, isn't there? It's going to get a little bit more involved. All right. Okay, so here we go on this one. So where do we start on these? So you see this on the test Monday, you say, okay, they're mixing them, I got to draw triangles, right? But this time, they're giving me 3x. Is that positive or negative? Careful, I'm asking you a trick question. Is that 3x? It could be either is the correct answer. It's got a letter. I don't know. I don't know what x is. X could be positive or negative, so I don't know what 3x is, huh? So I don't really know what quadrant's it in. Therefore, just put it in the first. Why? Because it could be anywhere if the x is negative, and that'll take care of it. When you're dealing with variables, the thing could vary. It could be anywhere. We don't know where it is. Just put it in the first quadrant and let the variables take care of where it really belongs. Okay. This is going to be pretty much the same. Just going to be with the letter. Let's take the inside. Now, 3x. Is 3x an answer or an angle? It's an answer, isn't it? 3x is an answer. So that means there's an angle, call it theta, and the sine of that theta is 3x. 3x is the answer. We good to there? So far, so good? Right? So sine inverse of 3x means regular sine of theta is 3x. Okay, now, Sohcahtoa. Let's go to the triangle. Sohcahtoa. Sine is opposite over hypotenuse. So that means I got to see this sine as opposite over hypotenuse. Well, I don't have it's not a fraction.
Over 1.
So you got to make it look like a fraction. This is like half of math. Is the plastic surgery. Removing the wrinkles, giving it a new look so you can do what you need to do. In this case, I need that thing to be a fraction so I can identify the opposite and the hypotenuse. Well, put it over 1. That's the same thing. I haven't changed anything. And now I can do what I need to do. This is opposite. This is hypotenuse. Put your theta here. This is the opposite side, the hypotenuse side, and the adjacent side. Okay, let's put it on there. 3x is the opposite. 1 is the hypotenuse. All right, so how do we find the other side? Pythag, right? Go do the Pythag. Here we go. A squared plus b squared is c squared. Which one of those is c? It's the one. It's the hypotenuse. So a squared. Now, if I write it like this, let me write it 3x squared like that. That's actually wrong. That is not the correct way to write that. What's wrong?
You have to put the parentheses around the 3.
Yeah, does that really matter?
Yes.
Yeah, because this way the 3 will get squared and become 9. The other way it wouldn't. That matters, right? Everybody good with that? Why is that correct? Because you're squaring the whole side, the whole 3x. So that'll become a squared plus 9x squared is 1. 1 squared is 9, huh? Everybody good there so far? Now it's easy at this point to lose and forget what we're even doing here. Why am I doing this again? Remember? You're trying to get your bachelor's degree, you had to take trigonometry. No, not all that. I just mean on this particular problem. We're trying to find the a, not the x. We could kind of lose our bearings and solve for x or something. Remember, we're trying to find a, ABC. We want it the other side, right? So it's a we want, not x, huh? We're trying to get a alone, right? The other side, the ABC, the other side, this bottom missing side. So we're trying to solve for a. So how do you solve for a there? Yeah, subtract or just jump over, subtract. You're right. You're right, Clarence. Subtract the 9x squared. Trying to get a alone, right? And then just square root it, huh? Is that good?
It isn't. Oh.
It's all good?
Wait, if you do. I did this really. My algebra is really, really wrong, but you can't just do negative 8x squared.
Oh, good question. Good question. Yeah. Yeah. Please ask that. I'm glad that's exactly an important question. Yeah. If that was 1x squared, you totally could. If that was 1x squared minus 9x squared, it'd be minus 8x squared. But if it doesn't have the x squared, they're not like terms, so they can't subtract. Great question. Yeah. I mean, that's all the stuff that I want to be able to answer for you to help. It's all that little algebra silly stuff that gets in our way, huh? So please ask it. That's what I'm here to do. Good question. Not only is that not true, and I want to say something else, but yeah, what else you got?
And if one has only one x, it's still the same.
Say that again?
If one has an x, it's still the same, or we can still like subtract it.
If one has an x?
Yeah, like 1x minus 9x squared.
Oh, like if that was x, yeah, I could not subtract it. Good question. They have to be the same power. I see what you're saying. Really good question. Yeah, they have to be the exact same power. Yeah, if I had that, I would have to leave that too. I couldn't subtract those either. Yeah, like terms have to have the exact same power to add or subtract.
So now that
Anything multiplies. Have you seen this theme of algebra? Adding, subtracting is super picky. Adding, subtracting, it's got to be like terms, common denominators, and on and on and on the list goes. If you just kind of put in the back of your mind for like all algebra rules, anytime you're doing adding or subtracting, it's super picky.
you can't.
And if
add
you're
and
multiplying or
subtract.
dividing, it's cake. Like I can multiply 1x times 9x squared, no problem. You can just do it. But with adding, subtracting, it's not. What was your question, Pauline?
It's like adding and subtracting apples and oranges.
Yeah,
You
it's
can't-
apples and oranges.
You can't
Exactly.
add them together because they're two separate.
Exactly what it is, yeah. Jose?
What's the step, how did you get down to, is that a squared or 9 squared?
Yeah, that's an a squared.
Oh, okay.
Yeah, this is my a here. It's unfortunate they put a 9 in the same problem with an a. Yeah, that's the square root of a squared, so that's just going to be regular a there. Yeah, we good to there? So this is going to be, let me bring it up here, the square root of 1 minus 9x squared.
So that's the answer.
That's that side, and I think that will be the answer, but let's get there in a second.
You can't simplify the square root.
Yeah, good. Other good question. That's exactly the one I wanted to do too, Angel. Yeah, look at that. Can't we just square root that 1 to be 1 and square root that 9x squared to be 3x, right? Right? It's not allowed. Why? Adding, subtracting. Remember what you want to have in the back of your mind? If you have adding, subtracting, it's super picky, and you can't square root those independently.
And the
You have to
root-
just leave it like that.
And the root can't cancel out the squared
It can't.
because of the one in front.
Pluses and minuses, yeah. The way I tell my algebra students all the time, pluses and minuses is like glue connecting things together, and you can't break the glue bond. It's just all kind of stuck there. So anytime you get things added or subtracted, you can't like just cancel that or just do the 9. Nothing like that's possible.
Could to figure out the whole 1 minus 3x, do we do the whole like equal 0 then do it that way or not? Let's say like that, and you put equal 0, then like, we could bring the 1 to the other side.
Well, yeah, if we had an equation, this isn't equal to anything though. Right, this is just, it's not equal to anything. There is no equation here. It's just it alone. Yeah, so we're not solving for x. Yeah, it's not an equation on that. Was there a question over here? We good? Is that making sense? Now, so everybody, that's a really good. There's a temptation to kind of just try to root that root. That's wrong. You can't do that. Everybody see what I'm saying there? That's not allowed. Now, I don't want to just say it like that. Let me just prove it to you. What if you took whatever? How about 16 minus 9? If you really could square root them, wouldn't that be 4 minus 3 or 1? But it's not. It's the root of 7. It's not 1. See how it's not true? I'm trying to show you that when you have plus or minus, it's not just a weird math rule. It's just not true. Right? If you could square root them separately, it would be 4. Right? Square root of 16 is 4. Square root of 9 is 3. It'd be 1. But it's not. It's the square root of 7. That's not 1. See how that's just simply not the truth, is it? When you have adding or subtracting in the middle of the root, it is not the truth to square root them independently. It changes it entirely. It's not just plastic surgery. It's a different person, right? So that's not allowed. Is minus the issue? Yeah, if that was times, it would be fine. Anyway, enough with all that. I better move on with the problem. So where are we at? So now we're ready for the final question. What is it? Cosine on the outside. That whole inside, sine inverse has just become theta, right? Because that's what comes out of an inverse trig function. As we started 2 hours ago, it just comes out theta. So what's the cosine of theta then? Going to the triangle. Cosine is adjacent over hypotenuse. Adjacent is that. Hypotenuse is 1, so it's square root of 1 minus 9x squared over 1, which is just the square root of 1 minus 9x squared. There it is. We did it. Questions on that? Is that good? All right. You want to try one of those? All right, so try that one.
Look what it gave me over here. The radical on the bottom. It's not correct.
It's not correct.
That's because you're not supposed to put the radical.
Oh, right. Yeah, they don't really care.
That's an answer, not.
But answers aren't supposed to come out with roots on the bottom, is Angel's point, which is true. They make us not give root answers on the bottom, huh?
No fair.
But they go ahead and go for it. That's right. Yeah, really, the truth is, there's no reason roots can't be at the bottom.
What's
So draw yourself a triangle on this one.
So we could just give the reciprocal, right?
See if we can get it to come out.
So it's root.
Because if you draw the triangle, you're going to get...
Yeah.
Right?
What's that?
It's just...
Oh, yeah, when there's
you
x's,
just skip that.
it's just first quadrant, because x can be a variable.
Before you did all
With
the
other
work.
numbers, like cosine inverse, if it's positive, always the first.
No, that's what I finished
If
it
it's
off.
negative,
And then I was like, wait a
then
minute,
you have to
cosine
put it
times
in
is
its other
reciprocal.
quadrant. So remember we learned cosine inverse is these first two quadrants. So for negative, it'd be the second, because positive is for the first quadrant.
Yeah.
So cosine inverse, if it was negative, would be the second.
Like
Sine inverse or tangent inverse would be right. So if they were negative, it'd be down here.
So this is the same
We'll
way?
never use it there for these.
No,
No.
that's.
No.
Darn it.
You wish.
You just draw a triangle in the fourth quadrant. If they gave you sine inverse or tangent inverse of a negative.
I just.
Yeah, we always use the first quadrant for positives.
I was gonna say,
because
it's the
it's
same
positive.
thing, it's just
So we use the
different.
first. But if they give me a negative number, if they, yeah, they give me a negative number. Yeah, right there. All right. Then I would do that. For cosine, negative is here. But if this was
How do you
tangent or
just
sine
split that
inverse
up?
of negative, it would be down.
So, sine. Just like opposite of what would overhead opposite.
Oh, yeah. There's nothing real clean to do. You would just put them together in a root. Just let them multiply together in a root.
Since it's not alike, because there's no x x squared in this one. I wasn't sure if I'm going to allow it.
Like, remember, anything like terms are for adding, subtracting. So you can't add or subtract them, but you can multiply anything.
Okay, wait, so this 14 minus x squared, we're talking because they cancel each other out when multiplying.
The roots?
Yeah.
No, only if they're the same roots. Only, okay.
Wait, so no, like
Can this
this
This is what I
and
did.
this
So I
multiplied
got,
together
like,
would
I
cancel
canceled out
out.
the radical
So it would be
squared.
14.
No.
that's what I was
So
thinking.
two roots only
And
cancel
then you
if
add
they're
the x squares together, you should get 2x.
Yeah, so that's what I meant by the like thing. Like, if they're not like,
And
obviously I don't know
then
what
square
to do
root,
with
square root again.
Yeah.
Yeah, I'll show you that one on the board. You just distribute in there. You just simply distribute and keep it in a
You
root.
take them all out, you get that works, right?
All right,
So x
let's
squared
take a look.
b squared equals this is on here.
So, Sohcahtoa. Sohcahtoa. Okay, so we're starting with sine inverse on the inside here. This means the sine of some angle. This is an answer, isn't it? Because it's being put into sine inverse, right? We put answers into inverse trig functions. So that means some angle, sine of some angle theta, is x over the square root of x squared plus 100. We good to there? I'm messing that up.
Mine was 5.
Because it's square.
Good to there so far? Right? So there's some angle, right? Because sine inverse, you put in an answer, there's the answer. And if there's some angle that makes that true. Huh? Okay, so now what is sine? Opposite over hypotenuse. This is opposite, this is hypotenuse. Let's go to our triangle. I'm going to make a triangle here in the first quadrant. Because I don't know, x is a variable, so I'll just use first quadrant. So the sine theta, so this is the hypotenuse, the adjacent side, the opposite. The opposite is x. The hypotenuse here is the square root of x squared plus 100. That's the hypotenuse. Good so far? Now, I got to find this other side down here, don't I? So that's the Pythag. So we use the Pythag. So we go a squared plus b squared is c squared. That is a squared plus, right? A squared plus x squared is c squared. The root of x squared plus 100 squared. Let me slow down there. Does everybody see what I'm doing? It's making some sense. So a squared plus b squared is c squared. So a squared plus x squared is the root thing squared. So what happens? A squared plus a, the root cancels the two. They're antidotes. They're like a poison in the antidote. They eliminate each other, don't they? That root and that 2 power cancel each other out, and you just get x squared plus 100, don't you? Everybody good to there? Is that making sense? Now we're trying to find a there. Trying to solve for a. Right? Remember, we're trying to find that other side, the third side of the triangle. The a. So what do I do to solve for a here? Get rid of the x's. Yeah, subtract the x squared. Gonzo, gonzo. So a squared is 100. Can you read it down there? I'm kind of running out of room. Bring it up here. A squared is 100. Root it. A is 10. The other side is 10, isn't it?
What are you rooting? Because the 100 up above doesn't have a square in it. You got rid of the square when you got rid of the root. The x squared plus 100.
Right. So there's no more square. Totally right, Jose. The square canceled the root, so those are totally gone. But I had the square that was still on the x, the 100, but the x's are gone now too. So it's just a squared equals so I know there's so much fancy stuff going on. Just think about, what if somebody said, hey, a squared is 25. How would you solve that for a? What would you do to turn it into regular a? You would root it, huh? The root would cancel the square, and regular a would be 5.
So even though it doesn't have a root on the 25, you still root it? I mean, a square on the 25?
Right.
You still got
I'm rooting it because of that square.
Okay.
I want to get rid of, even if there was a 7, by the way, over there, I would still root because that's what would make it regular a, and the root would just have to stay in the 7 because you can't root 7. Does that make sense? So it's just because of this 2 right here that I need to get rid of. The antidote, the opposite of it, is root.
Because you want a by itself.
Because I want a alone, regular a. Yeah, so right there I root it, the root cancels the square, so a is 10. So the other side is 10. Let's wrap up this problem now. What was in the very front here? Secant, and the whole inside, the sine inverse or the big old thing, that's theta, isn't it? Kind of move it down here out of the way. That's all theta, right? Because the inverse trig function, that's what they become. They just become an angle. That's what comes out of an inverse trig. When you put in an answer, you get out an angle for an inverse trig function. So out of sine inverse in the middle becomes theta in the middle. So secant of theta. Where's that? What's secant? That's cosines upside down, isn't it? Getting the hang of those by now? Starting to get those memorized? Secant is cosines upside down. So that's, instead of adjacent over hypotenuse, that's hypotenuse over adjacent. Upside down a cosine, huh? Hypotenuse here over adjacent 10. So square root of x squared plus 100 over 10. There it
You don't have to
is.
simplify that or
You can't.
or anything?
There's nothing more you can do.
10
Yeah.
and 100?
No, yeah, because of the plus sign, right? Getting the hang of it, those plus signs, glue them together and make no touch. Yeah, if that was times, we could do some stuff. But pluses and minuses just kind of stick stuff together. There's no messing with it. Yeah, it's good to just think that way in general. Pluses and minuses, nothing nice ever happens. So there we go on that one. Is that making sense? Questions on that one? Ooh, about 20 minutes. I'd like to start the next section. So is that good? That's a pretty messy one. That's the last one. That's the hardest one. So I think we've covered that section thoroughly.